how a generator works. So that's what I did in the last class. So I would like to speak a little bit more about magnetic fields and about what magnetic fields are and how to look at magnetic fields. So now basically we have seen two kinds of magnets. We have seen two kinds of magnets. Okay, so we have seen permanent magnets, or there are permanent magnets. I hope all of you are aware of it. And now we have seen electromagnets, right? So if you have a wire here, there is a magnetic field around this wire. Okay, there is a magnetic field around this wire. Now if you have a charge here Q, there is an electric field around this. So before I move on, first good afternoon, and second, hope the screen is visible and all that. Hope the screen is visible. Yes, some messages regarding that. Yes, so the screen is visible and audio is also visible. Okay. Okay, so if everything is AU. Okay, so if everything is okay, then let me carry on with what I wanted to communicate. Now, do you see that if there is a current carrying wire here like this, there is going to be a magnetic field, and we see that the magnetic field is something like this. So yeah, so that is a magnetic field there. So now if you have a charge, there is an electric field around it, but the force is in this direction. The force is in this direction. Now if you take the sun here, the earth is there. The earth is there around it. It is moving around it. Basically, the direction of the force is this side towards the sun. Yeah, but dl is in this direction. That is, the earth is moving in this direction. So if I find out what is the work done by the earth in moving this full circle, work done by the earth in moving this full circle, then what will I see? What will I get? I will get that, look, force is always perpendicular to displacement dl. So work done, which is equal to integral b dot dl will, which is equal to f dot dl, that will become equal to 0. So the work done in moving this full circle by the earth is 0. So in all such situations where the work done in moving around a closed loop is 0, we call such a force a conservative force. We call such a force a conservative force. So what we can understand is gravitational force is a conservative force. Okay, gravitational force is a conservative force. I hope we are able to understand that. Now let's look at electrostatic force. So now you have an electron here which seems to be rotating around a charge. So again the force is in this direction. So if the force is in this direction, again the logic will be the same. Integral E dot dl will become equal to 0. So why will it become equal to 0? Because E is perpendicular to this. So again this is a electrostatic force. Electrostatic force is a conservative force. Yeah, so the definition of a conservative force, a force where the total work done in moving through a closed path, it need not be circle. You can do whatever you want to do, you do, as long as it's a closed path, there won't be any work done. So the net work done will be equal to 0. So you may put a circle here saying that over a closed loop, the E dot dl is equal to 0. And because E dot dl is equal to 0, electrostatic forces are also conservative forces. So we have two examples of conservative forces. So gravitational force and electrostatic force are conservative forces. Do you understand the statement? Can you make some notes about this? Yeah. Yes. So can you make some notes about this? Okay, so these are conservative forces. Now let's do a similar. Yes, I hope all of you are listening, and I hope all of you are making some notes. Now let's make a similar assessment about the magnetic force. Yeah, let's make a similar assessment about magnetic force. Now, when you talk of magnetic force, do you understand that if there is a wire here and there is a magnetic field here, B and DL are in the same direction? The magnetic field is along this closed loop. DL is also along this closed loop. So when I do this integral B dot DL, whatever happens, it is not equal to 0. Because it is not equal to 0, I can say it is a non-conservative force. Yeah, because it is not equal to 0, it's like friction. So if there was friction here and if you're moving in a circle, always work will be done. So an example of a non-conservative force is frictional force. Now another example of a non-conservative force is induced magnetic forces. So now if you see that here B dot dl is not equal to 0. Now because B dot dl is not equal to 0, what can we say? We can say that it is a non-conservative force. That work is done in moving around this particle, moving around the closed loop. Yeah. So I hope you are able to understand. Any questions? Yes. All of you, good afternoon. Wake up. So I hope you are able to understand this. Now, if you understand this, let's do one more thing. Let's do one more thing. So I have the same magnetic field. Same magnetic field here. So now what is the force? Suppose I take a charged particle around this. What is the force equal to? Q into V cross B. So do you understand that force is perpendicular to velocity? Yeah, force is perpendicular to velocity. So if force is perpendicular to velocity, what will integral B dot integral F dot dl give you? what will integral of f dot dl give you over a closed loop? That will also be equal to 0. So that is what we saw here in this case and in this case. So now it means that it is a conservative force. Do we understand? Suppose you take a charged particle and you make the charged particle move in this. So the earlier contention that we said they did is, look, there is no force acting on it. But now when you look at this whole example of q into v cross b, you will see that the force is perpendicular to velocity. Now because force is perpendicular to velocity, integral b f dot dl will become equal to 0 because force is perpendicular, right? It is f dot dv, I mean f dot v dt. So f dot v, f is equal to q v cross b. So this product will become equal to 0. So now it is meaning that it is a conservative force. So now because of this particular confusion that is coming up in the case of magnetism, we don't discuss this whole issue at all. We don't discuss the fact or the idea if magnetic forces are conservative or non-conservative. So because of this, we don't discuss whether magnetic fields are conservative or non-conservative. It can be proved they are conservative. It can also be proved that they are non-conservative. What are they actually? That is quite complicated, and that is what Einstein has tried to bring out in his theory of relativity. And the answer is, it depends on how you look at it. It depends on how you look at it. If you take a magnetic monopole and try to move it in the circle around a magnetic field, there exists a force and there is work done. But the truth is, magnetic monopoles don't exist, so you can't do it. Right? So if you go by that logic, one logic says that if there was a magnetic monopole, it is non-conservative. But magnetic monopoles don't exist. So the least that you can do is you have to take a charge and then move it. Now, if you take a charge and move it, there is a force on it, but that force is always perpendicular and the work done is 0. So it is conservative. Yeah. So now because of this confusion, we don't discuss this aspect whether magnetic forces are conservative forces or non-conservative forces. And it is because of this that we do not discuss about magnetic potential. So in electricity you had, in charges you had electrostatic potential, but we will never talk about magnetic potential. We will not talk about magnetic potential energy. We will say that if there is a magnetic field, there is an energy, and that energy is equal to half into L into I squared. This we will say, but we will never talk about magnetic potential or magnetic potential energy. Are we able to understand this? Can you please make some notes for yourself? Can you please read this thing again? Can you please understand that, look, this is conservative, this is conservative, this is conservative, this is not conservative. But when you look at it from a charge perspective, this also looks like conservative. So the electric field, whether it is conservative or not, is basically answered by this concept of relativity. So it depends. So that is all that I can say. And it depends on what? It depends on whether you consider charges or whether you consider monopoles. but monopoles don't exist. So the closest that you can come to is charges. Yeah. So if you guys understand this, then give some indication so that I will move on from there. Yeah. So magnetic monopoles basically don't exist, right? Okay. So if this is understood, I will move on. Yeah, only if you guys are responding. I don't know what are the others doing. Are you guys sleeping? Am I not clear? Yeah, am I not clear? You want me to explain again? Yes. Yes, Lavanya, Nilesh, Nihilesh, Pranav, Pranita, Varsha, Kadir, Prem. Okay, so good. If you understand, it's fine. So let's move on. So the next thing that I want to communicate to you guys is, look, there are two kinds of magnets. You have permanent magnets and you have electromagnets. So electromagnets, we have spent so much time and energy trying to understand electromagnets. Let's spend a little bit of time and effort and try to understand what is a permanent magnet. A permanent magnet is fundamentally made up of a type of material called ferromagnetic material. Okay, earlier days there used to be only one ferromagnetic material, and then they discovered that nickel has the same properties, cobalt has the same properties. So then they have come across these ferromagnetic materials. So ferromagnetic materials are basically permanent magnets, or certain kinds of ferromagnetic materials form permanent magnets. So usually you can go get a bar magnet, a permanent bar magnet. Typically it will be made up of iron. It will be made up of iron, and yeah, it will have a north pole and it will have a south pole. Yeah, it will have a north pole, it will have a south pole. If you take some iron filings and then try to push it around them, so the iron filings will basically come and then form some kind of loops of this kind, and these type of loops exist both the sides. These kinds of loops come up on both the sides, and then we say that this is the magnetic field associated with a permanent magnet. Yeah. Now unfortunately, not unfortunately, the lines don't stop here. The lines continue to move here, and then this is the whole thing. So unlike electric fields, which don't form closed loops, magnetic field lines form closed loops. Okay, excuse me, magnetic field lines form closed loops. Yeah, so there is a north pole, then there is a south pole. So when there's a north pole, there's a south pole. The field lines go from the north pole towards the south pole. So again, from the north pole towards the south pole. This is all outside. Inside, the field lines will be going from the south pole to the north pole. Inside the magnet, they go from the south pole towards the north pole. So this is how the magnetic field lines exist. Okay. So if you can just make some small diagrams, and then we will move on. Yeah, so if this is understood, then we're done. So we understand this. So they'll ask you to draw the field lines for a bar magnet. So they'll ask you to draw the field lines for a bar magnet. Okay, so once this is understood, then I will get some indication from you all and then move on. Why do we consider? Now, we don't consider, we are saying they are not possible. How do you find out the direction? Yeah, you can't, it is just an assumption. You can't find out the field direction inside a permanent magnet. It is just an assumption. It is theoretically, they say that it is like that. Basically, if you come with a north pole, north pole, north pole, north pole, north pole, when you come like that, and when it turns, then it becomes a south pole. So once it becomes a south pole, then it will push it back. Videsh, we have to focus. Focus. I have not seen the paper. I'll see the paper and I'll tell you. Okay. Why do we consider? We want to complete our theory. We just want to complete our theory. So here you have a north pole. So if you have north pole, that north pole will be pushed. Pushed is all that you know. So when the north pole comes this side, it will be pushed. It will then be attracted. It will then be attracted. Now you see the north pole is changing its direction. So as it crosses the south pole, it becomes, if you look at it from this side, it will become the south pole. So it will be pushed, and so it will go there. Okay. So theoretically, magnetic field lines form closed loops, and then this is how the field lines are for a bar magnet. So you should be able to draw this in the exam. You should be able to draw them neatly in the exam. So this is the direction. Yeah. Everything else that you learnt in the case of electric field lines works out here also. Two field lines don't cross each other. Then again, the density of field lines will tell you how strong the magnetic field is. Now here they form closed loops. So they may ask you to write down three properties of magnetic field lines. So first property is they form closed loops. Then the standard thing, two field lines cannot intersect. Then the third thing, then the two field lines cannot intersect. And then the third thing is that denser the field lines, denser will be the, or higher will be the magnetic field. Yeah, denser the field lines, higher will be the magnetic field. So these are some basic properties. Okay, so let's try to learn a little bit more about permanent magnets. Yeah, so now if I take a permanent magnet and if I suspend it, if I just suspend it from some point, what it does is it orients itself such that one pole points towards the north side. Whichever is the north, one pole, so there is one pole here, that pole will tend to point towards the north of the earth. Yeah, so this is what we call as the north pole. So that is how we got the terminology that it is the north pole. Basically this come from our sailors. So the first magnets were used by sailors when they were in sea and they had to find out which direction is north. So they would just take a magnet and suspend. So the direction in which the magnet would point is called the north pole. So we refer to that as the north pole. Now if you look at the earth here, and we say that the north pole is in this direction, now do you understand that the north pole is actually south seeking? That means it seeks for the south pole. So as far as the earth is concerned, this is the south pole of the earth, south pole of the earth as the magnet. So this is the geographic North Pole, this is the geographic South Pole, and slightly inclined to it is the Earth's magnet, Earth as a magnet, and the South Pole of the Earth's magnet is towards the north, and the North Pole of the Earth's magnet is towards the south. So when you take a magnet and when you suspend it, the North Pole goes and points in the direction of the North Pole, and the South Pole is in the direction of the South Pole, implying that this is the North Pole of the Earth's magnet and this is the South Pole of the Earth's magnet. Now, you know, deep inside the Earth, we have this molten metal. Now, because this molten metal is in a constant agitated state. Now, because of those constant agitated state, because of the movement of the molten metal inside the Earth's crust, that basically creates, that is, there are lots of free electrons, and it is the movement of those free electrons which can be treated like current carrying loops, and it is because of those current carrying loops that the Earth behaves like a magnet. Yeah, it is because of those current carrying loops, current carrying loops inside the Earth's crust, inside the molten magma. Okay, so that is what basically makes the Earth behaves like a magnet. We will look at this a little later. Right now, let's focus on our magnet which we have suspended. So when you suspend a magnet and the magnet is influenced by the Earth's magnetic field, it points to the North Pole on one side, it points to the South Pole on another side. Okay, so now this magnet is like a dipole. So just as I have an electric dipole moment, electric dipole moment, which is equal to q into the distance separating them. In our case, we were taking it as 2d, so 2qd. The same way, we have a magnetic dipole moment. Yeah, magnetic dipole moment of any magnet, if it's an electromagnet, it is referred to, or it is defined as NIA. N for number of turns, I for current, A for area. And if it's a permanent magnet, I can say it is equal to the magnetic pole strength into the distance separating the two poles. So I will say that there is a north pole here, and I will say there is a pole here which we will call the North Pole, and I'll say there is a pole here which we will call the South Pole. It's an assumption. It's an assumption that there is a pole here which we will call the North Pole. There is a pole here which we will call the South Pole, and if the pole strength is P, then pole strength into 2D is equal to the magnetic moment. Pole strength into 2 is the magnetic moment. Here, the units of magnetic moment is current into area. So, unit of magnetic moment is equal to ampere meter squared, and the units of pole strength is equal to ampere per meter. Sorry, ampere meter. Yeah, this 2D comes down to the yeah. Oh, sorry. No, correct. Ampere meter. I thought this is divided by, okay, it's pole strength into 2D. So that is the dipole moment of the magnet. And from there, I can say that the units of pole strength is ampere meter. The unit of pole strength is ampere meter. So we are actually making a comparison, between electrostatics and magnetostatics. Okay, so if this is understood, then I will move. But before that, why should we not sleep by facing our head towards the north? Our body also has lot of magnetism in it. Our nerves interact with each other because of currents between them, minute currents between them. So they say that those minute currents will get affected. As a result, you will have neurological problems if you face with your head towards the north. Some people have done it, they have faced it, so they say don't do it. Now next we'll have to come up. Yashika, you can end the session right away. There is no problem. Uh, Sir, will we learn about oscillations in LC circuit? Yeah, we will learn about everything. Have patience and move ahead. Yeah, so do you understand oscillations in LC is a part of the next chapter. But that's also deleted portions. LC oscillations are deleted for you. So we don't have to learn it, but we will learn it, not a problem. So let's focus on what's being done now so that we find it easy. Okay, so this is how you get it. So if you understand this, I will move ahead and then I will move on. Yeah. Yeah, so Jafran, you don't have to tell the people, you can just go and sleep. That's it. Hmm. Yeah, so if you understand this, then let's move on and then go ahead. So if you take a magnet and you place it in an external magnetic field, suppose there is a magnetic field like this. This is the north pole of the magnetic field, and if you take a bar magnet and place it, it will align itself such that the north pole is facing the north pole is on the south side and the south pole is on the north side. So that is what is happening in the earth also. Yeah, so a magnet orients itself in the direction of the external magnetic field. So magnet orients itself in the direction of the external magnetic field. So this is the north pole here. So the south pole goes that side and the north pole comes onto the other side. Now if you turn the magnet a little bit, and leave it, there is a torque acting on it. Because of that torque, this tries to come back to its mean position. Yeah, because of that torque, it comes back to its mean position. But before that, let me just say that theoretically, they believe that the magnetic monopole is situated a little inside. Okay. Yeah, if you write notes, you won't feel sleepy, but the time is such. So yeah, so if there is an external magnetic field, so if placed in an external magnetic, so first understand that this is a little inside. So if length here is equal to 2 times L, this length will be little less than that. So accordingly, it will be P into pole strength into 2 times L. So where this 2 times L is the distance between these 2 points. That is an assumption. It is an assumption that the entire so-called north pole, is also called as the positive pole. So this is the positive pole and this is the negative pole. So the entire positive pole is uh, is the entire positive pole is concentrated at this point, the entire negative pole is concentrated at this point. That is why when we drew the circuits, drew the circles, fields, we drew them like this, a little inside. They were all meeting inside. They were all meeting inside. So that they were all meeting inside. Yeah, so that's how we drew them. Okay, and then you may write down that when a magnet is placed in an external magnetic field, it orients itself in the direction of the external field. It orients itself in the direction of the external field. Okay, so if you understand that, then we will move ahead. Let me see what kind of questions are there. Sir, 2D is the length of the bar magnet, right? But I am saying that it will actually be little less than that. Okay, so so it will be a little less than that. Yeah. How do we find out the direction of the field lines inside a magnet? Okay, I answered all those questions. Yes. So if you get this, then we can move ahead. So suppose you have a magnetic field this way. Suppose you have a magnetic field this way. So this arrow indicates the direction of force. So direction of force on the North Pole. Okay, the arrow indicates the direction of force on the North Pole. So now suppose you keep a magnet here, a bar magnet here, such that this is South Pole, North Pole. So the North Pole will tend to, it is free to rotate about its center. So the North Pole will tend to go that way and the South Pole will tend to come this way. So that ultimately the magnet will align itself in the direction of the external magnetic field. So this is the North Pole, this is the South Pole. Okay. So this torque which is acting on it, I can say is equal to like what we did in the case of a dipole. It is equal to pole strength into 2 times the length into B sine theta. So now this is what I call as the magnetic moment. So torque will become equal to M cross B. So if a permanent magnet is placed in an external magnetic field, it experiences a torque, and that torque is given as M cross B. M stands for magnetic moment. M stands for magnetic moment. Okay, so that is the torque which is acting on it. So that is the torque which is acting on the magnet. Now, if you have a magnet already, and it is oriented in the direction of the magnetic field, now suppose you turn it by a small angle theta. You turn it, suppose you turn it by a small angle theta, you will be doing work done by external agent. So this work done by external agent dW will become equal to T d theta, that is torque d theta. So that is equal to mb sine theta d theta. Yeah, mb sine theta d theta. So now when you complete that integral, the total work done will become integral T d theta. Everything is same. We're just copying from electrostatics. So that will become mb cos theta within limits 0 to theta dash or whatever, theta to theta 0. So now when you substitute that, you will get it is equal to mb, it is equal to mb cos theta minus cos theta 0, and generally they take cos theta 0, the initial position, this way. So if this is the initial position, then that is what we represent when theta is equal to 0. So sorry, theta is equal to 90. So if theta is equal to 90, cos 90 is 0. So we say the work done is equal to mb cos theta. Now this work done is what gets into as a potential energy. That means if you turn it like this, you do work. How much work did you do? You did mb cos theta or m dot b. Now once you did that work and then you release it, what happens is this tends to come back. Now when it comes back, it comes with some kinetic energy. Now in this case, we can talk about a potential energy coming up because of a magnetic field, but we will still not call it a magnetic potential energy. We will say it is the potential energy of the magnet environment system or of the field magnet system, but we will still not call it a magnetic potential energy, because potential energy is spoken of only for conservative fields. We don't speak of potential energy for non-conservative fields. Okay, so if you understand this, so this is the first slide that I was trying to show. This is the first slide that I was trying to show, saying that there is a force, there is going to be a torque acting on it. This is the next slide I was trying to show, where I was trying to tell you that oh, I did something wrong. This I explained, this I explained, this I explained, this I explained. Okay. So before that, there is a torque acting on it. The torque is equal to the pole strength, whatever it is, into 2L into B sine theta. Yeah. So this is nothing but the magnetic moment. So magnetic moment into B into sine theta. So now I can say that torque is equal to M cross B. So when a magnet is placed in an external field, it experiences a torque. That torque is equal to M cross B. So please make sure that you are able to write this. The magnet orients itself. The magnet orients itself in the direction of the external magnetic field. The magnet orients itself in the direction of the external magnetic field. Okay, so this is what it is. Let me see, sir. Sir, 2D is the length of the bar magnet. Okay, so sir, the bar magnet in the field is always in stable equilibrium. Yes. So so is all non-conservative forces will give rise only to kinetic energy? No, 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 no. Non-conservative forces, no. Friction doesn't give rise to any kinetic energy. Friction doesn't give rise to any kinetic energy. Non-conservative forces are complicated forces. They result in loss of energy, but not in all cases. They don't, yeah. So this magnetic force is a complicated force. That's why we don't talk about this. That's why in your book, they have not given all this. Okay. So just trying to tell you that there is a parallel between electrostatics and magnetostatics. And if there are questions based on magnetic dipoles, don't worry about it. You already learned electric dipoles, so apply the same concept here. So this is the work done in moving a magnet by an angle theta. Okay. So if you understand this, then we can move ahead. If you have any questions, sir, in all forces will give rise to no. The kind of questions they ask you here is what is the dimensions of pole strength, what are the units of pole strength, then again what is the work done in moving it by an angle theta, and so on. Okay, so now if you understand this, so some small questions based on this. So if I take a magnet and if I suspend it, it orients itself such that the north pole is in this direction, the south pole is here. Okay, now I explain to you that if you turn it by a small angle theta, there is a torque acting on it. The torque is equal to m cross b, so it is mb sine theta. So this is equal to I into alpha, I for moment of inertia, I for moment of inertia. So if I is the moment of inertia, then mb sine theta is equal to I into alpha. So if mb sine theta is equal to I into alpha, I can say alpha is equal to mb sine theta by I. Alpha is equal to mb sine theta by I. So if alpha is equal to mb sine theta by I, this part of it, and it's a restoring force, it tends to go back, which is because it is in equilibrium. Yeah. So this mb by I can be written as, or can be equated to omega squared. So if mb by I is equal to omega squared, then I can say time period is equal to 2 pi by omega. So that is equal to 2 pi root over of I by mb. So the magnet starts oscillating. So the magnet starts oscillating with the time period t is equal to root over of I by mb. I by mb. Is this part understood? Please make notes about it. Please think about it. Okay. Why can we equate to omega square? Oscillations. You have to read the chapter on oscillations. Whenever force is proportional to, whenever acceleration is proportional to x, or angular acceleration is proportional to theta, then this constant is equal to omega square. Okay, so for small angles, the sine theta can be equated to theta. So alpha is equal to minus mb by I into theta. Why is it minus? Because once you leave it, it will go back. So it's in equilibrium position. So it will be oscillating about mean position. Okay, so this will give you the time period for oscillations. Sir, can we able to consider bar magnet as a rod to find the inertia? Yes. So it's a rod, so moment of inertia about the center will be ml squared by 12. So moment of inertia about the center will be ml squared by 12. So I told you now the time period is equal to 2 pi root over of I by mb, where m is the magnetic moment B is the external magnetic field. I is equal to moment of inertia. I is equal to the moment of inertia. Okay. So now the kind of questions that you can get is this, that I taken a magnet. So these questions have appeared in the JEE mains. These questions will not come in the NCERT. In the NCERT, you have only till here. This is there in NCERT. This is there in NCERT. So CBSE exams will have here. CBSE exams will have here. Okay. Now what I am doing comes only in the entrance exams. It doesn't come in your board exams. So now if I cut this, and then take half of it, if I cut this and if I take half of it and then I suspend it. Now what is the time period for oscillations for this? Okay, so we said T is equal to 2 pi root over of I by mb. So if you cut it into this, what will happen to I? I will become half because mass is becoming half. What will happen to the pole strength? Pole strength will also become half. So m will also become half. So now this half here will get cancelled. So there is no change in time period. Okay, there is going to be no change in the time period. Yeah, so this is how it will move on. Okay, fine. Okay, I'll stop here. We will continue on Monday and then we will work with it. If you have any doubts, I'll consider. Sir, can we consider bar magnet as a rod? Yes, I told you. Yeah, so don't worry, we will work on Monday. This week's paper, I don't know. Hope it is easy and then you all work well. Work hard, that's the only way. There is no other way. Yeah, okay, bye.